out of our mind actually.
So please complete it.
Yeah.
I have uploaded the PPT, so you can get the data from there. So I just make sure that you understand that what is this UV method, which is the transportation algorithm, and how to apply it.
In assignment already we use that method, like UV method.
Yes, yes. Okay. Okay. Fine. Okay. So any question from the transportation algorithm, transportation problem?
No, sir.
Okay. So we have seen this transportation problem, which is a network flow kind of problem, right? As you can see that there will be source nodes and destination nodes, and there are supply quantities. I mean, the flow of materials, through different arcs in the network, right? And essentially, depending on the supply and demand, you assign some flow to these arcs, right? So it's essentially a network flow kind of problem. But it has a special structure in terms of supply points and demand points, and some constraints are there, right? Now, in general, for the other type of where it is not supply and demand type of problem, but network flow is there, like from some source to destination. So from one point, either it can be from one source to one destination, or it can be from multiple sources to multiple destinations, and often it happens through a network. So like in the transportation problem, we have seen between the source and destination there is a direct link, a direct arc is there, which means that suppose if I consider these warehouse locations as the sources, so they have a direct road network or direct air network to the destinations, the demand points, right? Which is often not not practical. I mean, in many cases, it may be feasible when you consider uh, big cities which are well connected, right? So you can get direct arcs. So I would not say it is not practical. Rather, I would say that it is, it is not general. Uh, so if you consider such locations for which direct arcs are not possible, and it has to go via some nodes, which itself has some capacities again, then it becomes a problem. Okay, so I'll just give you an example. Suppose you want to transport material, some amount of goods from Calcutta to say some place in northeast. Okay, where say for example I would say you can take an example like say Itanagar, Arunachal Pradesh, right? Now in Itanagar there is a small airport, and it doesn't allow big aircrafts to land. Okay, so what you have to do if you want to transport material, suppose you want to transport 10 tons of some product from Calcutta to Itanagar. So one option is you use a big aircraft from say Calcutta to Guwahati, and then from Guwahati you transport it by road, right? By renting, hiring trucks and other road transport services. This is one way. Another way could be that you suppose only air transport is available, no road transport is possible because of some say disaster situation or roads are blocked. So in that case, what is the solution? The solution is that you assess that what is the biggest aircraft that can land on Itanagar airport, right? And it may carry, say, for example, 5 ton, maximum 5 tons of load. So then what you have to do from Calcutta to Itanagar, although in Calcutta you can accommodate much bigger aircrafts having more capacity, load carrying capacity, right? But you cannot really send it to Itanagar because it doesn't have the landing facility there. Therefore, infrastructure, the CNPC number of the your airstrip, doesn't allow bigger aircrafts to land there, right? So what is the maximum quantity you can send? 5 ton only. So the constraint on at the Itanagar airport is actually restricting your choice at Calcutta airport. Although the Calcutta airport has much bigger facilities, right? Yeah, higher infrastructure. So we see, and also say if you can transport 10 tons from Calcutta to Guwahati, so Guwahati is also like an international airport, right? So you can transport 10 tons to Guwahati, and then from Guwahati you can deploy smaller aircrafts to Itanagar to carry 5 tons, 5 tons. So you have to make multiple trips, right? So this is another option. Now we see that in general these goods may be transported through these via nodes, right? Through intermediate nodes, and because of which there could be variations in the capacities. So we need to understand or we need to study in general how to handle network flows, how to solve network flow problems of general nature, right? So this is what we'll discuss today, general network flow problems and the solution methods, right? So how many of you already know about it, the network flow and the algorithms to solve it?
In our in algorithms course they taught Ford Fulkerson method.
Ford Fulkerson method. Okay. Fine. So all of you know Ford Fulkerson method?
I don't think everyone knows because it's only taught in algorithms course.
Okay. So it is better that we discuss again, so that those who know can know it better, and those who do not know, they will have some idea about what is network flow and the algorithms, the related algorithms to solve it. Okay. So can you see my screen? Just one moment. Yeah, this whiteboard is visible.
Yes, sir.
Okay. So what I do, I always take an example and then try to explain the theory underlying it. Okay. In that way, it becomes easier to understand. Because otherwise, if I just start the algorithm and the different steps, it will be very hard to connect that what is going on. Some theoretical notations and the pseudocode and all those things. So all those things are fine, they're there in the textbook, but it is more important to know how to apply them, how to solve problems with the help of those algorithms, right? So I'll start with an example. Say I consider this network S 1, 2, N. So this is a directed network. Why I am saying directed network? Because directed networks are more difficult to solve than undirected ones. So I'll always, we will always take the examples of directed network. Okay. Okay. So say this is the network. The source is S and the destination is n. And there are two intermediate nodes, 1 and 2, and the network is given. So each these directed edges, directed arcs, so they represent the possible direction of flow in the network, and each of these edges or arcs have some associated capacities. That means what is the maximum amount that can flow through it. You can consider it as an airline network or a rail network or even a water distribution network, a gas pipeline network, and many other things. If you can, supply chain network, anything you can consider it, right? So the problem here is that what is the maximum amount I can flow from the source to the destination. So this is called max flow problem. Okay. Maximum flow problem. Right. Now, why this issue is coming, that what is the maximum flow? Because each of these arcs will have a capacity, say Kij. It's denoted by Kij. So Kij is the capacity of the edge or the arc Ij. Right. So capacity of the arc Ij. Okay. So I want to know what is the value of f, maximum value of f that is possible. So suppose, for the time being, you just, you assume that you do not know Ford-Fulkerson algorithm, okay, or any other algorithm which can work it out. Suppose you only have the knowledge of linear programming. So how do you solve it using linear programming?
For each node, we can write constants.
Right. So what will, first of all, what is the objective? What will be the objective?
Maximize f.
Right, maximize f. Here f is the decision variable and you want to maximize. So this is the objective. And what will be the constraint? So for each node, we have to write, as you have said very rightly, that for each node we have to write constraint. Now, what constraint you have to write?
One constant is incoming flow should be equal to outgoing flow.
Right. So
And
that is
another,
called flow. That is
yeah,
called flow conservation or flow balance
yeah.
constant at each node. So we'll be assuming that except for source and destination, no intermediate nodes will hold the flow. That means nothing can stay at the intermediate nodes, right? And whatever is being supplied from the source should be delivered to the destination. So it should not be like there is any surplus quantity at the supply or excess quantity in the, or lack of quantity, slack quantity at the demand, right? So whatever is being supplied will be supplied, and no intermediate nodes will hold the flow, right? So these are some assumptions of this network model, So these are called flow conservation constants. Now for each node you try to write the flow conservation constants. Suppose for the source node S, what should be the constraint for the source node S, the flow conservation constraint? So F is the flow that we are trying to decide. So F is available at the source, which is getting distributed to 1 and 2, right? These are the two possible ways it can get distributed, and right. So if I denote these flows as fs1 and fs2, right, the flows that are flowing through these arcs, so then I have a constraint fs1 plus fs2 is equal to what? F. Assuming that the source will not hold any flow, so whatever is available it will supply the other nodes, right? Do you agree with it or not? So similarly, can you tell me what will be the constraint for node 1? So for each node, we have to write flow balance or flow conservation constraint. Otherwise, what if you do not include these constraints, your linear program may give a solution where it may say, at node 1 there will be some flow. I mean, the total incoming flow may not be equal to the outgoing flow, right? Which is actually practically not possible. So that is why we have to explicitly write these constraints. So tell me, what will be the constraint for node 1? Very simple.
Fs1 plus F21 equal to F1n plus F12.
Right, Fs1 plus F21 is equal to F12 and
F1n.
Right. So you see, these are the incoming arcs. You see, just see the incoming arcs and the flows associated with them, and the outgoing arcs in the flow. So similarly, you can write for node 2 and node n as well. Okay, which are F21 plus F2n equal to Fs2 plus F12. Sorry, this one is written already.
F12 only, sir.
Yeah. F12, yes. And what about this last node n?
F1n plus F2n equal to F.
Plus F2n equal to F. Okay, so these are flow conservation. So some flow conservation constraints. Objective is there. Any other constraint?
Capacity
Constraint, right? So you have to make sure that these flows should not exceed the capacity available along that arc. We know the capacity value Kij, so this is an input to you. You know these values, right? And these flow variables, so you have to restrict these flow variables if Ij should be less than equal to Kij, right? For all Ij pair, right, in the network. And it should be greater than equal to 0 also, because flow cannot be negative, right? So now this is the decision. So these are this is another constraint called capacity constraints. Okay. So now if you solve this LP, you will get the solution. You will get the maximum flow that is possible, right? But as you can see, although nowadays the computers are, the computational power is available and software is available, so you can simply actually you can code it, write it in some software like Simplex or um, any other software, and actually can get the solution very quickly for small problems. But as you can see that this LP has only equations, right? So again, while solving, what you have to do, you have to either take this two-phase approach or the dual simplex, right? And interestingly, this has less than equal to constraints as well. Unlike the transportation problem, while we had only equations, here you have a mix, equations as well as less than equal to constraints, right? So now our intention is to find out any other alternative method which is more efficient than simplex, which you can actually through which you can actually get this optimal result in a polynomial time. Okay, much easier way. So that is given by Ford-Fulkerson, which is known as Ford-Fulkerson algorithm, which we will now discuss. So is it clear up to this point how you can formulate the maximum flow problem as an LP and solve it by using simplex?
Yes, sir.
Okay. So now
Yes,
we
sir.
go to the next This is also known as Ford-Fulkerson algorithm. But before discussing Ford-Fulkerson algorithm, we have to first understand some basic concepts about graph and the cutting planes or cuts, they call it. So what is a cut in a graph? So in this graph, for example, how do I define a cut? Define a cut. S and S bar. Right. So if I draw a cut like this, say, is this a cut?
Yes, sir.
Yes. Why? Because it is cutting the graph into two portions. In one portion, the source node is there, and another, the destination is not there. You cannot cut a graph. You cannot think of a cut. Suppose, is this a cut? Is this a cut?
No, sir.
No,
No.
because
So neither the
basically
source
a
nor the
cut is defined as a division of a graph, so that in one division the source node is contained and another division contains the destination. This is how you define a cut. Okay. So now, cut is now defined. So here, for example, if I try to define this cut, this red line, dotted red line, what is S here? So if I say S and S bar, what is S here? S is small s 1 and 2, right? So small s 1 and 2, right? And what is S bar? Is
And
the destination, N. So this is how you define a cut. And essentially for a cut, this S intersection S bar should be 5. So there should not be any overlapping portion. That means no node can be common in these two sets. So now you can imagine how many cuts can be thought of for this graph. So for example, this is also a cut, right? Isn't it? This is also a cut. This is also a cut, right? So like this, many cuts can be, many cuts are available for a graph, right? Okay. Now I am defining another term before we go into the Ford-Fulkerson algorithm, that is called capacity of a cut. Cut capacity or capacity of a cut. How do you define the capacity of a cut? Say for example this one, S and S bar. So what is the capacity of this cut?
Sum of capacities which will like the edges which go from S to S dash.
S to S dash, right? So basically it gives you an idea that how much flow is possible through this cut, through this, so essentially this cut consists of these two edges, actually 1 to N and then 2 to N, which is flowing toward N, toward the destination, right? So what is the maximum flow that is possible through this cut is equal to the total capacity, sum of the capacities of these two edges, 1 to N and 2 to N, right? So capacity of this cut would be the K1N plus K2N, right? So this is the capacity of the cut. Some value, some quantity, constant quantity will be there, right? So we have now understood the capacity of the cut, and what it actually says, the meaning of it, that this is the maximum amount of flow that is possible through this cut, isn't it? right? So now we go to the fourth question. It is also known as max flow min cut theorem. Max flow min cut theorem. Okay. Or this is developed by Ford and Peterson. Generally, as we see that in general, what is this theorem? So in general, we have observed that flow F, right, is less than equal to the cut capacity. Can I say this? Any flow, F, is less than equal to the cut capacity for any cut. Intuitive, right? Now I am saying this flow F is actually less than equal to minimum cut capacity. Do you agree with it or not?
Yes, sir.
Whatever may be the flow,
Yes.
F should be equal to the minimum cut capacity. Because if you have many cuts and their cut capacities are different, but they are all separating the graph into two portions, right? So you cannot have a case where the flow will exceed the cut capacity of a cut. So instead of considering all cuts, we just focus on the mean cut, right? So flow F is less than mean cut capacity, and then it is very logical to draw this conclusion that the maximum flow through this mean cut would be the maximum flow through this mean cut would be actually the maximum flow for the network. So Ford-Fulkerson gives a very simple statement, which is this maximum flow through the network is equal to the mean cut capacity. So any flow that is feasible should satisfy this one, that is less than equal to mean cut capacity. And when you are trying to maximum limit of that flow will be equal to the minimum cut capacity. Now this can be proved theoretically, but I think we can skip that because it is quite intuitive and very easy to understand that why this theorem holds, right? So max flow is equal to the mean cut capacity. Okay. Based on this theorem, they developed a labeling algorithm which tries to assign flows along different arcs, satisfying the capacities, right, to find the maximum flow, which we will now discuss. But the theorem is this one. So the algorithm is known as the labeling algorithm, Ford-Fulkerson algorithm labeling, and it is based on this theorem. That is, the max flow is equal to the mean cut, which will be also reflected in the algorithm, the final result also, right? So is it clear up to this point about the theorem, what it is trying to say? Clear or
Yes,
not?
sir. Yes, sir.
So now we go to the algorithm, that is the labeling algorithm. Now, as usual, I will not go into the theory of it, of the algorithm and the steps. I will simply take an example and explain how to apply that algorithm and what are the steps will be explained with the help of this example. Okay. So let us take an example. Source is and N is the destination, right? Now say 2 intermediate nodes are there, 1 and 2, and so this is the data. Okay, so this is the data about the capacities of the arcs. So I am interested to find out what is the maximum flow F that is possible, right? So for this, they have developed a labeling algorithm. And how to label it? Label the graph. So first, what you have to do, you have to label the arcs. So we do the labeling in this way. So first we assume that the zero flows is going, right? F equal to 0 initially. Initial basic feasible solution, right? 0 origin, right? F equal to 0. And we label the arcs like this 0, 9, 0, 7. So which means in the label, the first one is the flow along that arc, and the second one is the capacity of that arc, right? 0, 9, then this is 0, 3, right? And this is 0, 8. Labeling done. Now, so this is a feasible solution, isn't it? F equal to 0. So it's a feasible solution. But what is our objective? Objective is to maximize the flow. So you have to increase the flow, right? So you have to find one from one corner point to another corner point, which improves the value of F, right? Now here, what we do, we try to find a path through which the flow can be increased, and it is known as flow augmenting path. Right? Augment the flow, add the flow. Right? And what is the flow augmenting? How to find it? You just find a path in which you can increase the flow by some amount. That's all. And you keep repeating it till the point you do not find any such flow augmenting path. For example, here, if we see what could be a flow augmenting path, we see that what is the remaining capacity in the arcs. For example, if I take this path, right? If I take this path, can I add any flow through this path? Is it possible to add any flow to this path? From F equal to 0, can I add F equal to 1? Can I increase 1 unit or 2 unit or 3 unit?
Yes, sir.
What is the maximum I can increase?
3.
3, because it is limited by this capacity of this arc 3. So you see, this is where, from origin you try to find an adjacent corner point. So you choose one basic non-basic variable to enter and try to increase as long as it hits some other boundary, right? Constraint boundary. So it is very similar here. So from F equal to 0, you try to increase F till this capacity is restricting. So which means here the maximum flow is F equal to 3, right? So you assign F equal to 3. So through this path, we assign F equal to 3 through this path. So the moment we add 3 units of flow through this path, we have to update the levels, because now some flow will be there along some arcs, right? And then remaining capacity will have to be adjusted accordingly, right? So what will be the updated here? Updated network. So now I have added 3, F equal to 3, right? So now it becomes 3, 7. This is 0, 9 because it is not the part of augmenting path. Okay, here it has become 3, 3, right? And then N, here it has become 3, 8, and here it has become, it is the same 0, 9. right? F equal to 3. So this is the revised graph. So another corner point, BFS, where F equal to 3. Now flow has increased from 0 to 3. Okay. So now you have to find another augmenting path. Is there any other path through which flow can be increased? So you consider this one. Any path you can consider. So for example, if you now consider this path, right? Is it possible to increase the flow along this path?
Yes,
Yes
sir.
or no? Yes. How much?
7.
So F equal to now 4 you have to add, right? Along this augmented path. So F will become 7 total. So now you can update this network again, right? So you will get a relabeled network, right? Which is this one. So I'm just clubbing two steps. So F equal to F will become 7. So it will become, so this will become actually 4 7, right? This will become 4 9, isn't it? So this will become 7 and this will become 7, right? Now, so you get the now you have to again find another augmenting path. So it is easy to see that if you now consider this path, right? This one. Can you increase any flow through this path? Yes, capacity is available. See 3 8, so 5 units are remaining, right? Here though 9 units are remaining. So what is the maximum you can send through this path? 5, right? F equal to 5 through this path. So again it gets added. So F now becomes 12, right? So you get a modified network, which is this one. So F becomes 12, right? Now an interesting thing will come. So 7 7 and then 3 3 and then 2 and then this is 5 9 and then n, this is 8 8 now, and now this is 4 9, right? And here F12. So currently this is the situation. Now tell me that can I even increase the F of 12 or we have exhausted all the options?
We can still increase.
Why? How?
First we take a flow from S to 2, a
Mm-hmm.
flow of, and then we can reduce the flow from in this 1 to 2 edge. We can actually reduce the flow,
Mm-hmm.
and if we do that, we have more capacity left in the 2 to N edge.
2 to
N edge, we can have some capacity. If instead of flowing from S to I, then I to 2, S to 1 and 1 to 2 and 2 to N, we can, if you take S to 1 and 1 to N directly.
Mm-hmm. Right. So here this concept of backward একটু এই ক্লাস নিচ্ছি একটু পরে 15 মিনিট পরে আসুন, হ্যাঁ 12টার পর, ঠিক আছে? হ্যাঁ. So here see apparently it seems that so what is the augmenting path we will consider here, right? So not necessarily you will have to always consider an augmenting path with forward flows or with forward arcs. You can also have an augmenting path with backward arcs. What I mean, so if you consider this path as an augmenting path now, right, this one and this one, right? So here you see these three, these arcs are all forward arcs, but what about this 2 to 1? So I can see 1 to 2 there is an arc, right? I mean there is a flow. This is a directed arc. So 1 to 2 is a directed arc, and through which I have already assigned 3 units of flow. right? So now you are seeing here what is the remaining capacity? 4. And here what is the remaining capacity? 5. Right? And what is the capacity of this arc? 3. So if I consider this augmenting path, what is the maximum amount I can flow through this path is 3, because its capacity is 3. Right? But this flow would be backward, isn't it? But it's a forward arc. So when I try to flow through it backward, in a backward manner, so essentially we'll be reducing the flow through this arc, right? So currently this flow is 3. So if I try to flow 3 units from 2 to 1, it will actually reduce this flow by 3 units. So it will become 0, 3. So although mathematically we are seeing in an augmenting path, but actually no flow is happening from 1 to 1. Are you getting my point?
Yes, sir.
So this is the provision, this is one provision in this leveling routine, in this algorithm, that you can also consider backward flow by reducing the flow. Okay. So, and that is also limited by the capacity of the arc. So 3 units, if I try to flow F equal to 3, additional 3 units from here to here, and then, so then in this arc, it will relabel this as 0, 3. Again, these will be relabeled as 8, 9, right? And these will be relabeled as 7, 9. And these will be relabeled, this backward arc will be relabeled as 0, 3. Okay. Now you will see that you have exhausted all options of adding the flow. So F has become now, with the addition of 3, F has now become 15, right? So F is now 15. And all augmented paths are exhausted. So you cannot increase the flow, even by 1 unit. You cannot increase. Okay. Then what is the solution? So solution is F equal to 15. That is the max flow, right? And and these last levels, that is the latest levels, will give you the distribution of the flow. So finally, what is happening? This F equal to 15 is available at the source. So 7 units are going to 1, and then 7 units are going to n, from 1 to n, right? 1 to 2, there is 0, 3. That means there is no flow using this arc, right? And then S to 2, 8 units are flowing, and 2 to n, 8 units are flowing. So these 15 units are getting divided in this manner. And finally, this 1 to 2 arc is not being used at all. Any question or any problem with this?
No, sir.
Okay. And can you verify whether this is actually the satisfying the theorem that max flow is equal to the mean cut? So through this algorithm, we have got this max flow 15. Now, what is the mean cut for this graph?
S and 2 on one side and 1 and n on the other side.
Right.
1 and
Right. So this is the mean cut actually. This is the mean cut. And what is the cut capacity for this? 7 plus 8, which is 15. This arc is from S bar to S. So we are not considering this arc, right? Because cut is defined as the capacity of the cut is defined as the sum of the capacity of all arcs from S to S bar, not from S bar to S. So this arc is from S bar to S, so we will not consider it in the capacity calculation, right? But we will consider this as a part of the cut, that's fine, but not in the capacity. Okay, so now 15, 15, so we start. So this completes the labeling routine given by Ford Fulkerson. Okay. So now some questions are there. So what happens when we have undirected hours? So same problem, say we have undirected hours. Then how to handle those things? So say I have this kind of graph, say S, and then say 1, and then 2, and then N, right? Simple. And then I have an undirected edge from 1 to 2, say. So how to apply Ford Fulkerson routine, this labeling routine to this?
Like we can replace that undirected edge by two
Right.
directed edge, like both are opposite direction but
Right.
have same capacity.
Have the same capacity. Very good. And if at the end, if you see, say this is F12 and this is F21. So at the end, if you see that if F12 is greater than F21, right? So which means that actually there is some flow from 1 to 2 have with quantity F12 minus F21, right? So at the end, you have to interpret it like that. Okay. And what happens, another variant, just then I'll close it. What happens when you have multiple sources and multiple destinations? So instead of say S, you have S1, and then S2, S3, three sources, and then three destinations, N1, N2, and N3, say. And you have a network like this, right? Like the transportation problem, right? You have a network like this connecting these destinations, right? So then how do you apply?
Add a dummy source and connect all the sources to it, and add a dummy destination and connect all destinations to it.
Yes. So add a dummy source and then connect all the sources from here, and then add a dummy and then connect all this. Very good.
And capacity is infinite, like very large.
Capacity is how much?
Very, like ideally it should be infinite, like because we don't know the maximum amount which can come. So
No, so we have to assign some capacity here, na? So it will be a very big number.
yeah, very big number.
Because finally the capacities of the other earths will actually restrict the flow. So you don't have to worry about it. Right? Okay, good. So this was about the Ford Fulkerson algorithm, and now in the next class we will discuss the shortest path problems in networks, Dijkstra algorithm, and the minimum spanning tree problems. Right now, because I have a sense that I have a feeling that some of you are already familiar with it, so I want at least some of you to come forward and present your understanding about Dijkstra, how to solve shortest path problem on directed arcs, and the minimal spanning tree problem using Prim's algorithm, right? Or some other algorithm is also there. Can you present it tomorrow? Dijkstra and Prim's. One for shortest path, another one is for minimal spanning tree. So who can present it? You have to prepare a PPT actually, because you don't have that whiteboard, no? The writing facility. Do you have anyone has got the writing pad?
I have, sir. Like in online we can use actually. It's there actually.
So can you present tomorrow?
I can present the extra.
Dijkstra. So Dijkstra you present, and then who will present the minimal spanning tree, Prim's algorithm? Present means you will present and then we'll discuss. Okay, others will ask questions and we'll discuss basically. Who else can present minimal spanning tree, Prim's algorithm? Who is from computer science? Any person who has taken algorithm course? What about Ashutosh Dash? You're from which department?
Aerospace, sir.
Aerospace. Achha. Who is from computer science? Shoumen Dotto?
Yes, sir, I can do it.
Yeah, you can do it. Okay, good. So Prim's algorithm, you also prepare. You have a writing pad?
No, I'll prepare a PPT.
So you prepare PPT. Okay, good. So see you tomorrow then. Let me download this.
Sir, and one more thing regarding Saturday's class, I have an extra class at that time, so 3 to 4 of other subject.
Which one?
Saturday.